Hello everyone, my name is Nam. I am a master student at Sorbonne University. I'll be presenting our work in trec 2022. This work is done in collaboration with Saclay in Montreal University. We propose a new approach in conversational retrieval. Previously, most methods use a query rewriting step, then ranking and re-ranking. We propose to bypass the query rewriting step. We leverage SPLATE, a sparse retrieval model, for end-to-end first-stage ranking, and also for selecting keywords for re-ranking. The SPLATE model encodes a text, either a query or document, into a term importance vector. SPLATE is already trained, so we suppose that the document representation is good. We encode the query in its context as follows. There will be two representation components, one encoding the query in context of its past queries, the other in context of its past answers. Here is an illustration of the information flow. The top branch reads queries, and the bottom branch reads one answer. Q-hat queries is produced from all queries. The model treating this concatenation of queries is SPLATE, parameterized by theta queries. For context from last answer, we have Q-hat answers is produced from the current query and each previous turn's answer. Because one answer may be very long, we encode each pair of query answers separately. Essentially, for each past answer, we ask, how can this answer enrich the current query? We average out the representation from each turn. The model doing this computation is SPLATE, parameterized by theta answer. Through experimentations, we choose to only use the most recent answer. We train by aligning query representation. A simple training loss is just a mean squared error. We compute the target by using SPLATE on the manually rewritten query. This turns out to not be good enough. The model does not capture well information from previous answers. And so we propose an asymmetric MSE designed to encourage term expansion from past answers. We want to punish the second component, which reads the past answers, only when it fails to capture terms and not when it overweights terms. Formally, the loss is computed as follows. This asymmetric loss only applies to terms present in the manually rewritten query. So intuitively, this loss pushes the answer contextualized representation to capture terms from the manually rewritten query while imposing no upper bound constraints. We simply add the two losses up. There is interplay between the two losses. The asymmetric loss pushes up the weight of the tokens present in the manually written query as much as it can, whereas the standard MSE loss then compensates and takes care of all the other tokens. So this puts extra focus on extracting information from past answers. I will now present the re-ranking step before talking about the data. We adapt the T5 re-ranker to the conversational use case using keywords identified in the first stage. For this stage, we do use an enriched query, but not rewritten by a sequence-to-sequence model as usual. This is just a concatenation of queries and some keywords. We will use the T5 mono approach. The motivation is that if the T5 can do re-ranking and it can do rewriting, then it should be able to do both at the same time. So how do I get my keywords? They will be words identified as important by the first stage ranker. We only consider words in previous queries or previous answers, and in our case, it will be just the most recent answer. A word's importance value is the highest importance value given to any of the tokens that composes it. And here we will take 10 keywords. The T5 mono re-ranker directly gives a score for each query answer pair, so we can fine-tune by just matching the scores. We can get a gold score using the manually rewritten query and the original T5 mono re-ranker. So we start with a simple MSE loss. Alternatively, we can use the MSE margin loss. This operates on the margin between the good document and the bad one, rather than the raw score of one single document. We train our model using the TrekCast 20 and 21 dataset and the Carnot dataset. Because Carnot answers are short, very different from TrekCast ones, we lengthen them using the ORConfQA dataset. This dataset contains the Wikipedia article from which Carnot answers are extracted. So if we want passages of 4 sentences, we can just grab 3 extra sentences from ORConfQA. Here is an example of a TrekCast answer, which is very long, and a Carnot answer, which is very short. And here is the Wikipedia passage from which that Carnot answer in red is extracted. So here we took a longer snippet in brown to use as answer instead. We make sure that the position of the red text in a brown snippet is uniformly random. So either the first, second, third, or last sentence. We submit 4 runs. First is just the first stage ranker. Second is with re-ranker trained with MSE loss. The third one is the same but trained with MSE margin loss. And the fourth is just like the third, but with 3 re-rankers and ensemble together. Notice the only difference between the 3 models is just the sampling of training data. We report our result in comparison with the organizer's baseline. We see that even the first stage ranker does basically as well as the baseline while being very fast. The recall is 2 times bigger and the NDCG is 1.5 times bigger. MSE loss for re-ranker is bad. It's actually even worse than not re-ranking at all. And the MSE margin loss performs well. It reaches above 40 NDCG cutoff at 3, which is better than the baseline. To conclude, our pipeline consists of 2 building blocks. The first is conf-splay, a fast neuron first stage leveraging splay. Here we retrain the query representation model so that it takes into account the conversation. And the second is a lightweight re-ranking, where we use keywords identified by splay. So thank you for listening.